The work that I'm going to present is dealing with the wrinkling phenomenon in soft membrane created with additive manufacturing, and it is a study in cooperation between NTNU, University of Parma, and La Sapienza University. The presentation is divided into six sections to recap the phases of our research process: motivation, material, methods, results, and conclusions. The production process of leather uses outdated techniques that require a significant amount of resources and generate a lot of waste that, if improperly disposed of, can harm the environment. Therefore, the new developments in this field for a more sustainable approach. The use of materials that resemble leather may offer a solution. In fact, they can improve the quality control and usability while requiring fewer dangerous chemicals and natural resources. To achieve a realistic leather-like membrane, new technologies like additive manufacturing can be used to print a large variety of forms and patterns. This will help to reduce raw resources consumption, speed up the manufacturing process, and most important, improve quality control. Wrinkling on leather capture our attention. In fact, this phenomenon occurs daily on leather products. This phenomenon can be helpful in understanding how to recreate height behaviors on membranes made with additive manufacturing. With this work, we aim to address three main research questions: how to reproduce a membrane that resembles leather and mimic the structure of the hide, which materials are more appropriate, and how to reproduce the wrinkling in a membrane to mimic the behavior of tan. The structure, schematized in the right picture, is split in tanneries to obtain usable section for a good quality leather. The two first layers, grain and corium, define the top grain, a high-quality split. The grain near the surface has a compact appearance and has thinner collagen fibers, while the corium under the grain is characterized by thick fibers. To recreate a leather-like membrane that mimics the structure of the hide, we substitute the top grain's layers with a two-layer membrane that resembles the structure of the top grain. This allows us to define a clear subdivision between the film grain and the foundation corium. To choose the more suitable material that can provide good bonding and mechanical properties similar to or even better than leather, a literature review was carried out focusing on learning how the hide structure was recreated and tested to evaluate the mechanical properties. Considering the knowledge gathered, PLA and TPU are the materials that we choose to recreate the hide structure. The first material, polylactic acid, also known as PLA, is a thermoplastic polyester. This type of polyester material is known to be degradable. This behavior makes PLA environmental friendly. Moreover, the production process uses less energy than producing conventional plastic and generates fewer greenhouse gases. The second material involved is thermoplastic polyurethane, or TPU, which is referred as the bridge between rubber and plastic. It is widely used in industry for components and coating, but also for 3D printing. The production process is also known to be easy, leading to a material with good abrasion property. The production process of leather-like membrane, which should adopt a more sustainable approach than the tanning process, is another factor to be considered. A practical method for fulfilling this requirement is 3D printing, also known as additive manufacturing. By precisely depositing material layer by layer, we can use this technique to turn a computer-aided design into a physical object. The A4V4 printer, a B-material printer, is used to create and print the specimens. The quality control performed on the specimen printed evaluates the filament's adherence, the effective extrusion rate, and the pattern's sharpness. The design and G-code writing were performed using full control and SSI software. The layer thickness for PLA is set to 0.15 millimeters, and the specimen was printed using a nozzle with a 0.3 millimeters diameter. We can set an infill density of 100% in the SSI software, but it doesn't take the printer's characteristics into account. This issue will be covered in the printing results section. The extruder temperature ranges from 210 degrees for the rough to 200 degrees for the specimen. The bed temperature is maintained at 60 degrees. The wrinkles on the soft membrane will be triggered by a compressive force acting on the substrate. Therefore, a compressive mechanical property evaluation for rigid plastic was carried out following the STM guidelines. To prepare the specimen so that the mechanical properties can be used to describe the behavior of the B-layer specimen, we reproduce the same printing pattern and loading condition as in the leather-like membrane. The specimen used to evaluate compressive mechanical properties are printed with a ±45-degree patterns. The test specimens were designed in compliance with the STM regulation, which provides standards for specimen dimension for strength measurement. As a result, the specimens have a prismatic shape with a length twice its principal width, and the specimen is rotated so that the ±45-degree layers are parallel to the printing plate. The diameter of the PLA filament are 2.85 millimeters, and the nozzle dimension is 0.3 millimeters. To better describe the mechanical properties, 5 specimens are tested, aligning the principal axis with the load axis, and the speed of testing is set to 1.3 mm per minute. The compressive machine has a load cell of 100 kN, and the data acquisition is performed using Catman software. The mechanical behavior of a thin film resting on top of soft elastic foundation has been described using the analytical tool that we use to comprehend the principles that govern the formation of wrinkles. The thin film is firmly adhered to the infinite thick elastic foundation and has a thickness and width of h and w. We don't take into account the shear stress between the foundation and the skin. Instead, we only consider the elastic modulus and the Poisson ratio for the two materials. The compressive force in the skin is given by the first formula on the left. Lambda denotes the sinusoidal deflection profile of the skin along the direction of the applied force, acting on the elastic foundation. Critical wavelength is observed when the load exceeds the critical value. The wavelength prediction method shows that the critical value for lambda is independent of stress and strain and only depends on the material characteristic and the skin thickness. As can be seen, when the skin thickness and the ratio of the two elastic moduli are low, the critical wavelength is small, but when these terms are high, the wavelength significantly increases. Numerical simulation is the second method. We use this tool to validate the analytical approach. We use Strauss 7 to recreate the soft membrane that has a 0.2 mm of skin thickness to reduce the influence of the infinite foundation. A skin-to-foundation thickness ratio of 1 to 50 is set in the numerical model. We will review the literature review as well as experimental data to compare the mechanical properties of PLA. We will perform linear bulking and non-linear. Here are shown the printing stages from the design to the printing. The 5 specimens undergo the quality test. All the specimens have a good filament adherence, there aren't visible problems with extrusion rate, and the printing pattern is good. The SSI software allows us to set the infill density to 100%, but it does not guarantee that all the layers printed have this standard. After a more detailed control, we notice that the fewer first layers printed on the supporting raft have an infill density lower than 100%, about 80%. This aspect highlights how the software used to design and generate the G-code does not take in consideration the limits of the machine used. The dimensions errors on the specimen are acceptable based on the printing properties. As shown in the picture, all the specimens after the test has the same deformation that was developed principally after the yield stress was reached. The stress-strain curves exhibit a linear response just after the accommodation of the loading plates at the initial stages of the deformation process. We decided to exclude the last specimen from the average value analyzed since the printer showed some failure with the cooling system. The compressive strength and elastic model are comparable with the ones of the literature review. The analytical analyses are validated with the numerical analysis. In fact, the two values of critical wavelength are comparable. Moreover, the mechanical properties of the literature are similar to the ones we observed from the compressive test. On the right, we have the results for the backlink analysis. We perform a nonlinear analysis to investigate the displacement increment trend. To trigger the distortion, we used an initial imperfection similar to the wrinkles distortion that we observed in the backlink analysis, reduced so that the maximum displacement was equal to 1/10 of the skin thickness. The outcome of this analysis highlights how the displacement increment relationship is nonlinear. In the picture, the development of the wrinkles is shown at the sign increment. The outcome of this work highlights how additive manufacturing might be a valid solution. In fact, we observed that the procedure adopted to design and print the specimen is rapid and only a small amount of recyclable waste was generated. PLA and TPU combined gave good results. The quality and mechanical properties of the two materials led to a good setup for the formation of wrinkles under a compression force. The analytical and numerical approach underline how the critical wavelengths have the same magnitude as the tan height. Further analysis can be done by printing the two material and evaluating the bonding and the wrinkling formation. Thank you for your attention.